Hi there. My name is Brennan Crispin, and this is my presentation on implementing SURF, speeded up robust features for ECE 588. So overview, I'm going to be talking quick summary of what is SURF and why I chose implementation of that algorithm for my project. And then I'll go into how SURF is used in feature detection, the approach for feature matching and tests and results. So what is SURF? SURF stands for Speeded Up Robust Features, and it is a local feature detector and descriptor similar to SIFT. It, however, uses several different approximations and some slightly different methods that it makes it faster and, according to the authors of the paper, more robust. So why? So we talked about SIFT in this class, and I enjoyed learning and found it interesting how it works, but I decided I wanted to get a better feel for how feature detectors work at the programmatic level, how you would actually code them to function. So since we'd already discussed SIFT in the algorithm, I decided I wanted to look at a different one, did a little research, and came across SURF, and so went with that. So the first part of SURF, being similar to SIFT, is that it has feature detection. And there are four major steps in feature detection with SURF. The first is the calculation of the integral image. The second is creation of Hessian matrices. Third is then taking that the Hessian matrix layer and applying it across the scale space. And then finally, we do feature point localization. So the first step that we have is the creation of the integral image. Now, integral images are a very useful tool that allow us for fast calculation of the average intensity of an area of an image. And as you'll see in a minute, a lot of the calculations used in SURF rely on box filters, which is a way to approximate the second order Gaussian. So when we're calculating an integral image, what we're doing is that we're taking each point on the in the image, and we are calculating the summation of all of the intensities above it and to the left of it. So the basic function of that would be the summation over x, the summation over y of the intensity of ij. However, for our implementation of this, what we'll do is we will take the integral over I, and then the integral over j. And what we'll do is we'll calculate, once we've calculated the initial intensity, we'll just take the intensity to the left and the intensity above. And by adding those together, then we can get all the intensities, like the integral image of that particular point. And so later then we'll also see that we can use the integral image to calculate a box, which for integral images, that is the we can call it the average intensity over that space with A, B, C, and D. So as I mentioned, for the in SURF, we're going to be approximating second order Gaussian using something called box filters. So on the left, you'll see the box filter that approximates the second order Gaussian dYy, so the Gaussian in the y direction. And on the right, you'll see one for dxy and dyx. So you can see, looking at these, that because they have constant values over an area, that it will be really, really simple to take the to apply these convolution filters, but instead use the integral image over each of these areas and have a really, really fast calculation rather than having to calculate the Gaussian for each point surrounding our point of interest. We can instead use an integral image and do that in 4 calculations in constant time, which is going to save us a lot of time down the road. So, knowing this, we're going to begin by calculating the Hessian matrices. So, in the SURF algorithm, we're going to be getting a Hessian matrix and then calculating its determinant. And And that's how we're going to be using to measure the local change. That is to say, the feature points where the value is at maximum. And in the Hessian matrix, what we're going to be calculating is around each point, we're going to be taking this equation here in order to fill in the second order derivative in the xx direction, the xy, yx, and yy directions for a given point, and then you can see and then for the scale that we are currently at. And as a minute, we'll get to the actual scale space for this. And with the Hessian matrix, we're going to be using the integral image and the box filters to approximate the Hessian matrix. So we won't actually be calculating the second order derivative. We'll be using the box filters to approximate it for each point. And we're going to be starting with a 9x9 matrix. So if we pull up the Hessian layer, what we'll be doing is that we will be creating a series of these Hessian layers, which it's not actually the Hessian, it's the image, and then it's converted into a series of determinants for the Hessian matrix surrounding each point for a series of filters. And actually, we will, going here, when we build our difference of Hessian's map, which is very similar to the difference of Gaussian's map, except using the Hessian as a summary, what we're going to do is we are going to be creating a variety of Hessian layers at the various sizes. And I'll come to how the filter sizes are determined in a minute. So what we're doing is we then build the Hessian layer. So we're going to be calculating dxx, dyyy, and dxy. We can use dxy twice because they will be analogous to each other. And once again, we will iterate over each step in the matrix. In the image, we'll be calculating dxx using the box, the integral image, and calculating its the box integral, as well as that. Dyyy will be doing the same thing. Obviously, it'll be oriented inversely, and then dxy will be using the image to then calculate the boxes. So what we'll then do is we will calculate the determinant for each of those spaces, and we will then we have an array, which is all of the different determinants for all the different points in the image. You'll notice here there is a constant. Normally, if we calculate the determinant, it'd be dxx dyy minus dxy. However, the authors of the SURF algorithm found that putting a constant there of 0.9 improves the response. We also take the sign here of the Laplacian, which will be used for matching later. So once we have our first Hessian layer, we'll then apply it across the scale space. Now, in SIFT, we created the scale space by effectively shrinking our image using Gaussians and then taking the difference of Gaussian across each of those new images. However, unlike SIFT, SURF creates its scale space by applying box filters of increasing size. As you remember, we could apply box filters with comparatively minimal processing time, so it makes sense that we'd want to continue to apply them. And then the resulting we'll call them Hessian matrices, they're not actually Hessian matrices, but the resulting layers, we can then use a difference of Hessians approach, which we'll get into, to determine what the best response. As with SIFT, the scale space is divided into octaves, which are divided into layers, and each octave doubles the scale factor, so from 6 to 12, and then 12 to 24, and so on. As you can see on the right, we have the DYY, the YY box filter, and all that we've done is we've taken it and doubled its size from 6 to 12. Likewise with the XY box filter, we have taken it and doubled its size from 6 to 12. So if you look at the scale space, that's what we're doing here, is that we are iterating over the octaves and each layer in the octaves, and we are doubling the size, what we'll see is here is that we'll start with a 9 by 9, it'll go to 15 by 15, 21, 27, and then we'll loop back at 15, and then it increases by 12, 39, 51, 27, 51, 75, 99, and so on. The authors found that they really start running out of useful interest points after about 5 octaves, and so in our implementation, we also only used 5 octaves for our scale space. So once we've built this scale space of response layers, we need to find localize our feature points. So that's going to have 2 major steps. The first is that we need to find local extremum in a 3 by 3 by 3 space where the third dimension is the scale space. And then the second step is that we are going to build 2 matrices for each point, or for each interesting and local extremum, the derivative in the x, y, and s directions, and then we'll also create the Hessian matrix in those 3 dimensions. And then we will cross-multiply them and return us a matrix of responses in the x, y, and layer. And we will, if all 3 of those values in that matrix are less than 0.5, then we assign that point to be a valid feature point. So now that we've identified our feature points, we need to build our descriptor. And the descriptor for surf is based on Haar wavelets. We'll use them both to assign an orientation as well as to generate the descriptor. And on the right here, you can see a Haar wavelet. It's very similar to the box filters, except there's only 2 pieces. It's very, very simple. And if we look at the implementation of a Haar wavelet, we'll see we're just calculating the box for one side is positive, one side divided by the scale is positive, and then the other side is negative. We just subtract. Very, very simple, very, very fast, but it does give us a good response for what we're going to be doing. So in order to assign our orientation, we're going to calculate the Haar wavelet responses for all the points in a circle of radius 6s around our interest point. Once we've done that, we're going to kind of iterate through these pi/3 sized windows around the point and sum all of the responses in the x and y directions around that point. Once we find the window with the largest maximum value, we will take the sum of the x's and y sums and calculate the angle between them and return that as our orientation. So after that, we need to generate our descriptor. And descriptor, we'll find that by taking a square region of size 20s centered around the interest point. And the square, as you'll see in the image to the right, it's rotated with respect to the orientation that we calculated. And then that 20-point region will be divided into 4 by 4 subregions. And then within each of those 4 by 4 subregions, we're going to calculate the Haar response in a 5s window, where s is the size of the scale. And we'll rate that response with the Gaussian for the reason that I mentioned earlier. So when we calculate the Haar responses, we'll do the x and the y direction, and we will sum up all of the responses in that subregion. We'll take the sum dx, sum dy, as well as the sum of the absolute value dx and the absolute value of dy. And that is the descriptor for that subregion. Since there's 16 subregions and there'll be 4 responses, we'll sum them all up and we'll get a descriptor of size 64. Matching. So matching is not something I went into and implemented. I used some OpenCV libraries for matching. And for each key point, we used Flan, which is a fast library for approximating nearest neighbors, to get the nearest neighbor for all of the feature points in both images that we are matching. And then we filter out what are the ones that are too far away. Generally, we find the minimum distance between 2 nearest neighbor feature points, and then took and then only feature points that were no more than double that nearest neighbor distance were used. Once we did that, we used OpenCV's find homography function to compute a best fit transformation with a ransack to ignore some points that don't fit the transformation, and then we performed a perspective transform on both sets of points to get the matched object. So doing that, our goal in this project was I wanted to take street signs, and then apply them on a street image and recognize the sign. So we had a few different test signs: a one-way sign, a stop sign, a yield, a slow, and another slow children at play sign. And we had some successes with the stop sign was able to be identified here, as well as a little bit less successful with this yield sign. It was able to identify that it was present in the image and the location, but it was not able to accurately square off the yield. However, on average, for this, surf had a lot of failures. There are a few different reasons for it. I think partly is that because a lot of the signs, a lot of their features are basically end up appearing in multiple places. For example, in this image, you'll notice there's a purple feature point at the bottom of P, and it gets matched to the bottom of the T in the scene image, which makes sense because they're roughly the same size and shape, and so that it's going to be very similar feature points. You'll also notice there's a sea green in the bottom right-hand corner of the O that gets matched to the top right-hand corner of P. Once again, if you look at it, it's a very, very similar. The shape and the response there is going to be very, very similar, and because even though it's rotated. So overall, I found that, and here's another example of failure. Overall, I found that surf was not very appropriate for matching a generic street sign to an image. That's not, generally speaking, what I found that surf is used for in the wild. It's used for more unique object identification and tracking. So I went back and I did a few other, for example, I took a Cheerios box and then placed it within several other cereal boxes and found that it was very strongly matched. Another example, matching a logo to an automobile. And then even going back with one of the old versions that we did and taking the exact copy of the sign and rotating it, and it was able to match it without any trouble. And that was generally speaking the case. Is if there were unique features that were uniquely applicable to the image and to the object we were looking for, it was very easy. Surf did a really good job. Surf did a really good job of tracking it and identifying it. If it was a more generic feature that may not always apply to the specific object, but rather to like a class of similar objects, it didn't do as good of a job. So, for example, stop signs might have slightly different fonts, and the fonts might have identical features across multiple parts of the letters. It did not do a great job. And that kind of matches up with how surf gets used. It's great for video, tracking an object within video. It's much faster than SIFT. And because the object is not changing, it's just moving, it was very good at tracking it. It's also used for creating 3D images in order to stitch. You take multiple image pictures as you're rotating around image, and it would be very strong at stitching together adjacent elements. Thank you.